Okay, so first, thank you for being here, for being in this seminar. This seminar is about vector search, and this is the flow I'm gonna walk you through today. First, I'm gonna talk about what is this seminar about, and um, a sequential of algorithm. Okay, as you can see in the screen, this is a simple retrieval system. Like we have the content pass it through a deep learning model to get a vector embedding, and then we search in vector database. Uh, a bit about disclaimer. This seminar only focus on how to like index vector to create vector database, like how to build vector database and how the search process works. Yeah, not about how to like embedding vector efficiently. Okay, the first algorithm is low quality sensitive hashing. Um, in the indexing process, we have the vector indexing right here. We pass it through some function. We call it hashing function, and it will return for us a ID. We call it bucket ID, right? And the second step is bucket filling. We store the vector based on their predefined ID. Uh, okay, so in either and about hashing function, um, it must satisfy some property like it has to locality sensitive. It can be any function that can map similar vector into the same bucket. Uh, Even like it just can, it just satisfies that it can map similar vector into the same bucket. Yeah, and so it can be any function. And in reality, LSH use multiple hashing function, like to increase the accuracy and the complex of the function. Like we don't want we don't want it to, much simple. Okay, so in the searching process, we like input is query vector, output is bucket ID. Like we also pass the query vector to through the hashing function to get bucket ID, and we only calculate the distance with the vectors in the same bucket, so it decrease so much the number of vectors that we need to search if we compare to like L2 if we compare to flat index. Basically flat index will like compare the query vector with all vector in the database. So so the process of compute distance with vectors in the same bucket will decrease the search time a lot. um, okay, so after that we get the result. uh, we choose top k nearest neighbor as our result. Okay, that is the first really simple algorithm. So anyone have any questions? Go ahead. Okay, okay, wait for a second. Okay, the next algorithm is a bit more complex, um, which is a hierarchical navigable small world graphs. Uh, Basically, it is the combination of skip-list theory and navigable small world theory. Okay, the first is skip-list. Uh, you can see on the screen, skip-list has some properties like each layer is a linked list, like it had several layers, and each layer is a linked list. And the lowest layer, like the layer number 0, contains all the data points, and the higher layer is, the more sparsity the connection is. Like we have less connection if we see in the layer number 3. And how it works, like we start the search from the highest layer. Like we have the query vector, right? We start the search in, like we want to search the element 20. We start search from the layer 3. We see that the next node, like we moving down, if the next node is null or larger than the target, so we see that this is smaller. So we see that the next node is 7, smaller than 20, so we move to the next. So we choose it in a current node, and we see that the next node of this current node is null, so we move to the layer number 3 and number 2. So we see that the next node is 15, smaller than 20, so we move down one layer. We do not move, and we choose this at a current node, and we see that the next node of this current node is 28, larger than 20, so we move down. We see that the next node is 21, so we move down. So that is current node right now. So the next node is 20, so yeah, we find our target. Any question?
How do we get the blocks like this? Like, how do we get, like, when there are 7 and there's 4
Okay.
blocks above it?
Okay. I will, like in the context of linked list, I do not read about it, but in the context of vector search, maybe I will talk in the next slide. Okay. I like how to build this kind of node.
A little bit confused here because it is splits, right? So, what type of structure?
Sorry,
Type
but
of structure this is? Maybe this can be a list, like in Python, maybe a dictionary or something like that. And one is more specific.
okay.
Can you
Sorry,
talk
Nguyen,
about
but I cannot hear you clearly. Is it the same with Hà Lan or Đức Anh?
that? Okay.
Can you like talk a bit louder?
Okay.
Okay, clearly.
Over here, a little bit confused about what is skip structure. Maybe it can be a list like in Python or dictionary or array, something more specific about structure.
Okay. Like skip list is contain multiple layers, and each layer is a linked list with a current node and a next node. Okay.
Yeah, because a little bit confused about linked, right? Because linked is not for searching. Linked is not good for searching. It's only good for it's good for something more direct. Yeah, like when you try to uh, have a not when you have a not good memory in your computer, so you will need to skip in the SSD or SSD. This can be much more better, right? Maybe I think about this list can be a very large quantity, so we need to use list to reduce the RAM, right?
Yes, yes, yes.
Okay, okay.
Okay. Skip lists alone perform search very poor, as you said, but if it compared to like navigable small world, yeah, it's much better. So let me explain this navigable small world. basically it's a graph. It's a graph. Each node represents a vector. Yeah, and how to build it? First, we have a data set of vectors. For example, we shuffling data point and inserting them one by one. And when a new node is inserted, it is then linked by edge to m nearest vertex to it. So for example, in this case, m equal to 2. Okay, how it work? So first, we inserted each node one by one. So first is node A, and then node B, and we only have node A in the graph right now. So we have to link node A and B together regardless of their similarity. So we have node C, because m equal to 2, so C will link to 2 nearest neighbor to it, so B and A, and we got D, and we repeat the step until we build all the data points in the data set. Okay, okay, so how to search? Okay, so first we need to choose a random entry point. So in this example, this is node A, and we we have the query right here. This is our query, and then we compute distance to its connected vertices. Like the connected vertices of entry point is B, C, and D, and we compute distance of D with the query. B, C, D to query, and then we found that D is the closest, so we choose D as our next entry point. So yeah, we repeat the algorithm, and when the algorithm cannot find a node that is closer than the current node itself, and it stops. Maybe I will stop for a second for you to think about it, but I think it's quite simple right now.
This algorithm is much more like digital, right?
Sorry.
This algorithm is look like digital algorithm.
No, I think it looks like a greedy routing more. Like it search all the neighbor of the entry point BCD and calculate distance to all of them, which is greedy, and then it choose the closest distance as the next
Yeah.
entry point. So it's
But I
routing
feel that
right.
is follow the sources route in digital from H to L like that. So Paris much closer to L, so A is need to find the shortest time. Yeah, it's like the digital.
Yeah. Okay. Okay. Uh, okay, that is navigable small world and skiplets. So it and HW will it's a combination of it. We inherit the layer property from skiplet, and each layer we have navigable small world. Okay. So each layer is navigable small world in, instead of node in linked list. Okay, instead of linked list. Um, Okay, and search begins at the top layer, like the linked list. We search at the top layer, move down, and the lowest layer will contain all of our data points. And at each layer, we'll perform the search like navigable small world. And and as we move down to the lowest layer, we have a list of visited nodes, and we just choose top k nearest neighbor from this. Okay, okay. Uh, for like how to build, to answer the question of Halan, how to build the layer in this algorithm is like just build is like how to build the navigable small world. It's exactly the same. But how to choose the node in each layer is it's like a bit complex, so I will not mention it here. But basically, you can choose it's random based on uniformly distributed, formally distributed. Okay. Okay. The next algorithm is invert 5, which is also very powerful. Uh, the concept of indexing is we have a bunch of bunch of vector in our data sets. So we perform some clustering algorithm like k-means, or more advanced is DB scan to find the centroid. Okay, and once we have the centroid, we assign an index, like exactly like how k-means work. Okay, so we have a vector over here will be assigned index to this centroid, and this region is called Voronoi cells. And what cool things about invert5 is that we can even apply LSH or HNW in each Voronoi cells. So people usually combine uh, the algorithm with inverted files like EVF and HNHW, which means that we apply HNHW data structure at each Voronoi cells. Okay. Okay. So how the searching works? We have the XQ, which is the query vector, and we find the nearest centroid to the query. For example, in this case, this is the nearest centroid, and we only compute distance with vectors which is in the region of centroid, which means this region. But we can modify it with the search scope hyperparameter, which is nprop. In this case, nprop is equal to 1, but we can also set it to 8 so that we can search at a more larger region. Okay. Okay. So that is 3, very basic algorithm in a vector search uh, domain. So do you have any question before I move to the next part? Okay. So this part I'm gonna talk about quantization in vector search. Like it's really important concepts, and almost every search system or search engine apply it. Uh, okay, so let's talk about the why. Uh, okay, given database of 100 million data points, and each vector will have dimension of 1000, and with data type is float 32. And so for the storage, we need to storage. Um, sorry, this is this dimension. So for the storage, we need to store this, large storage capacity. And for the search, we cannot load all at once because of the RAM. We cannot like build the RAM up to 1 terabyte. So there are several techniques. The simplest is you add the models that has smaller embedding. The second is load in batch. Like we have a bunch of vector database and we load in batch. So for example, we first load this batch and we calculate the distance and store it somewhere, and yeah, again repeat the iteration. Okay, and the most popular technique and also the most efficient techniques is quantization. I will talk about vector quantization and product quantization, also scalar quantization. Okay, sorry, I cannot find any figure or image that represent it well, so I will talk it in text. Okay, so vector quantization. Imagine that we have a vector of 100 vector with dimension of 2048 dimensions. So first we need to create a codebook. Codebook is like list of centroids. We apply some clustering algorithm to our vector database. So we have list of centroid, right? So yeah, they call it a codebook, and each centroid they call it code words. Okay, so if we have a list of a code word, a code book, so we like replace each vector in a data set with the index of nearest code word in the code book. Does it make sense? So for example, we choose k centroid. So our codebook will have the size of k and this dimension. So for example, we choose k equal to like 50. So this is our size of codebook. So we replace each vector in the data set with the index of nearest code word. So our vector originally right now be converted to this kind of small vector database. So it reduces the storage a lot. Okay, so for the searching process, we encode the query. So the query will have the size of this dimension, and then we and then we encode it to 1 and 1. Okay, and then we calculate distance to this vector database to choose the nearest neighbor. Is it okay, anh em?
Okay.
Okay. About product quantization. Okay. About product quantization. Suppose you have a vector of this dimension, like this dimension. Okay. Here is how it works step by step. So the vector is divided into 64 subspaces, and each of which is 64 dimension. So we want to have this output after we split it. Okay, so we apply vector quantization in each subspace independently. Okay, so we will have this dimension after all. Okay. Okay.
So sorry, but I don't understand the table. Why one is lower, shorter, and good, and one higher, longer, and better. I don't understand. Even the memory efficiency, right? So what difference between good and better?
Okay, which mean that vector quantization is good at storage, but product quantization is better when compared to vector quantization.
But in the table only two, right? So why one is good and one is better? Maybe the table will need to change a little bit, right?
So you ask about why the product quantization better than vector quantization?
You can answer that later, but the table is not too specific, right? I read the table and not even not even a sign to me to understand the table.
Uh, okay. I, I I understand that you wonder about the scope of the table, but in this table they are just compare these two algorithms with each other. So better mean that product quantization better than vector quantization at memory efficiency.
Yeah, okay.
Okay. Um, okay, let's just have some calculation to prove why product quantization is better. So suppose this dimension, if we use vector quantization, uh, sorry, okay, vector quantization will quantize this vector to this dimension, and product quantization will quantize it to this dimension. So basically, the vector quantization will better at memory efficient. Sorry, but the for accuracy, the product quantization is higher, and also the search time is very fast. So people prefer to use product quantization more. Okay. Okay, so for scalar quantization, it is easier to understand than the previous. Uh, it is when you want to quantize float 30 to like in 30 or sorry in 8 or something. So reduce 4 byte to 1 byte. Uh, okay, so you define the range. Suppose that 0 to 15, and then you choose the number of levels like equally interval 0, 5, 10, and 15. You compute the bin size, and each number in the range of 0 to 3 will be quantized to 0. Okay, that's how scalar quantization works in vector search domain. Okay, comes to the uh, most important part in this seminar. I want to introduce the scan algorithm, which is come from Google research team. Okay, so this is the quantization objective, right? This sign mean in the product, and Q is query, X is vector. So and X here is like quantized vector. So we want to minimize the this loss, right? Okay. And if you notice that all the calculation by then is all based on L2 distance. Like vector quantization, we apply some clustering algorithm, right? And for example, k-mean use L2 distance, and scan found that it's not fair to use like L2 distance. So we want to introduce the new loss function instead of this loss. Okay, so let's talk about why it's not fair. Mm, okay, so L2 loss will uniformly minimize quantization loss across all vectors, right? Because it just take the L2 calculation. But in the context of such system, we do inner product between query and vector database like this. So if inner product is different with L2, so they use inner product to identify the relevance. So at the example here, you can see that the query number 1 is greater than query number 2 and query number 3 in terms of inner product with the vector x. So they ask the question, is it better to increase the weight of this inner product in quantization loss? Um, is it better for quantization when focusing more on high relevance interactions? Like if we use L2, so the quantization loss is equally distributed. So L2 will consider this, and this is equal, but we want like the inner products, uh, but we want to focusing more on the high relevance interactions. So we want to quantize this query vector more. Okay.
I understand this because product is much more focused on the angle. The
Yeah,
angle in
exactly.
high dimension product, we can call it like consistency. And in L2, it's only calculates distance between several nodes. And I think that's the reason why they choose inner product, because inner product is much more efficient in higher dimension.
Okay. Yeah, exactly. So they want to change the quantization loss. Traditional quantization loss is use L2 calculation, but now they introduce another score over quantization loss, which is focused more on inner products. Yeah, that's how they calculate it. And I will not explain deeply about this because we are AI engineer. And okay, I think this seminar, uh, I will try to make you understand the intuitions about the formula rather than proof what is the meaning of the formula and how they form it. So yeah, so so that's how score over quantization loss come into play. So you can understand that uh, for the query that you know uh, closer to the vector, so they will increase the weight of quantization loss, which means the loss of this kind of pair quantization will contribute more to quantization loss. So they apply this idea to view the quantization loss. Uh, okay, so input of us gonna be this is x, this is a original vector, this is quantized vector, and this is weight. Okay. Okay. So in the indexing process, scan use three data structure. The root will represent the entire data set. Okay, so next step is partitioning the data. Each node in the tree splits data into smaller subsets by using k-means, which means we have the roots, we have k-mean, for example, k equal to 10, so we have 10 leaves at 10 leaf. Okay, so we repeat it until predefined number of leaps or certain tree depth is reached. Okay, so we apply quantization, product quantization with score aware uh, to our tree. So we perform vector encoding, which means we will transform this dimension to like this dimension. For example, if we choose the hyperparameter subspace, it is 64. Okay. Okay. So in the searching process, we perform tree traversal. Sorry for misspelling. And at x left, we computing the distance from the query point to all point in the leaf. So we have, for example, 3 leaf, and this is our query point. We compute distance to all of them. Okay, so we, for example, m equal to 1, so we choose one closest vector to traverse down. For example, we choose this vector. Okay, so we traverse down, move down, and repeat the process again. Okay, so that's scan call it a quick scoring because we only compute distance uh, in the quantized vector, like we compute the very small vectors with each other. So scan call it quick scoring. So, and in order to get the exact scoring, so they will choose the top results from the initial scoring phase, which will be rescored to refine the accuracy. So they will use original vector like this vector to compute the inner product to get the exact accuracy. Okay, so and then they will choose top nearest neighbor. Okay, any question? Okay. The top results from the initial scoring phase will get from the visited node. Okay, so this is the results by the time scan was released. It achieved state-of-the-art performance on this benchmark. So you can see that it applied so much the quantization technique in its algorithm. So the speed queries per second were really high, like outperform all of the other algorithm. So this is scan, and this is maybe this is HNW. Okay. By the way, scan is the best. Okay. This is all of the seminar about. Actually, I want to add some more parts like rule of thumb, like uh, sorry, like rule of thumb, whether to choose which when the algorithm choose based on what case, like okay, but I do not have time, so this is all of the seminar. Okay, so this seminar I cover about several, like the vector search algorithm, how to indexing, how to create vector database, and how to search it, and the state-of-the-art algorithm. Do you have any questions?
So is this algorithm used in most vector database now, or is it just some research?
Okay, okay, to answer your question, the algorithm that is most in vector database is this algorithm. It's like the most popular and the most kind of it's really powerful. Like if you there are some vector database that I know is Wavia and each and attributes is wrapped up quite well in Wavia vector database. Okay, and yeah, so this algorithm is used the most. And but if you do not wanna waste your money into vector database and you want to store and search in local server, then you have to apply some quantization technique to reduce the storage and the RAM, the memory cost. Okay. Okay, so talk a bit about your topic at Viettel. Um, so like you have a bunch of video, right? Okay, so you must somehow create this bunch of data set into vector database by using uh, some techniques I mentioned here or other techniques. Yeah, but yeah, so you have basically the indexing process is the most important in the vector search domain, and the indexing really affects how we search. Like each indexing algorithm has its own search, right? Okay, any other question? Okay, so that's the end of our seminar. So thank you for being here. Thank you so much. Okay.